All right, good morning, everybody. Happy Monday. So we have really about, I guess, 2 more weeks left in this semester, looks like, because we have this week. Next week is Thanksgiving week, which we'll still have that Wednesday, that Thanksgiving Eve class, because I guess it's a morning class and it's also online. So that really can't really affect any of your Thanksgiving sort of traveling and whatnot. So I guess I could have a class next Wednesday, 8:30. And it looks like based on how I have the semester mapped out, after that we'll have on Monday, we'll have the Monday after Thanksgiving, we'll have our final exam review. And then Wednesday could either be a canceled class or could be just an extra Q&A session for whatever, let's say for a final exam or for whatever, I guess. That wouldn't be an actual class, but depends on if the demand is at least one or two people at least are interested to have some type of Q&A session. At least then I'm not, canceling class officially, but there's no new material left, or I could do extra exam review. But then again, I don't think the final exam is going to be so dense with stuff. But of course, we could see how that goes. But for now, we have really 4 more lectures of new stuff left. So I have a new assignment posted up on Canvas. I'm not going to really go over it in class because it's actually very simple. So read through the handouts, very simple program. So I'll just sort of discuss it just for a second right here. So basically, I have this class called Priority Queue, just so that way it's has some deception to it. So it could be a min heap or it could be a max heap. You decide if you want to make it a max heap or a min heap. And also, there is a class in the C standard library, or sorry, the standard template library called priority underscore Q. So I had this class name as priority and then the capital letter Q at the end, so it's not to be distinguished, or not to be confused with that STL priority queue. So it'll be a min or max heap. And you want to find the kth biggest element in that unsorted list of numbers in that file. So that file, you're going to have a number at the very beginning, which will be k, which that means you want to, let's say if the number is like 7, you want to find a 7th biggest number. If a number at top is 10, then 10th biggest number. Then you have several numbers, which is going to be using end of file control loop. And you want to find the kth biggest number. But rule is you don't want to sort the array. You don't want to put everything into the heap at the very beginning and then just sort of pop the heap k number of times. You want to kind of do it in a way where, assuming that you don't know how many elements are going to be in the file, so you kind of want to update them, update the kth biggest element as you go. So as you're reading elements in one by one, you want to update the kth biggest element. So actually in code grade, I actually had it where you output the kth biggest after every time an update happens where you have a new kth biggest number, it outputs that to the screen. Just that way you're kind of forced to not be able to just sort it and so forth. So that's really all there is to that assignment. Very simple, not a hard program by any means. So it's very similar, I would say, to assignment 6, which is that recipe hash map, similar to that. So assignment 9 will be a little bit harder because it will involve graph theory. It's going to probably be a depth first or breadth first search type sort of structure. I'll have that assignment all done by midweek or so, and that'll be due probably on that Friday of study week. So you'll have enough time to work on that. So that way, definitely we'll get everything done, and you won't be rushed towards the end. That's why I'm making this assignment due within a week, so you can kind of begin the ninth homework right after. I'm not going to push back assignment 7, probably assignment 8 probably either, because there's no need to get a week to work on a program that really might take you a few hours or maybe a day or two. Just don't. It's you first have to write the code for a min or max heap, but it's really yeah, and really it's actually I went over sort of how you would think about the code for it. So remember how to get the parent index, left child, right child, using that symbol formula, swap two numbers in the heap array. Just don't really think it's that hard of a program. So yeah. So anyway, I guess now I'm going to go ahead and now talk about, I'm going to continue with some stuff. So we have 4 lectures to give. So today I'll go over some applications of depth first search. Wednesday will be breadth first search. Next week, Monday will be Dijkstra's algorithm. And then Wednesday will be Kruskal's algorithm. So that's kind of our map of this semester. Let's go ahead and begin right here. So I'm going to start a screen share. And let's begin. Okay, so I went over depth first search the other day. So basically a very simple traversal of a graph. It's just basically all we're doing in depth first search is we're at a node and we just pick an edge to go to, try to explore a new node, and then we back up if we hit a dead end, or once we process it. Let's say we're at a current node and we already traversed through all of its neighbors, well, then you have to back up to the previous node and continue. So it's really just pre-order traversal extended on a graph. That's the only difference. And we have to use these four um, parameters or data structures to implement depth first search. Now, the predecessors is kind of optional. That is used to compute the paths. I wonder if I actually went over a predecessor example the other day. How to use predecessors to actually find a path. Let me just see if I actually went over that. Oh, I did. So if you do want to actually output a path to node 5, you start from 5, you push 5 onto your stack. Then 5's predecessor would be 2, push 2 onto your stack. Then 2's predecessor is 1, push 1 onto your stack. 1's predecessor is 0, put 0 onto your stack. 0 has no predecessors, so the stack from top to bottom is your path. So use that predecessors array to construct your path, basically. That's why you need it. You don't need that necessarily, but if you want to actually construct the actual path, then that's what you actually have to use a predecessor array to construct your paths, basically. Okay, so now I want to go over an application of depth first search. One of them will be finding a cycle in a graph. Let's go ahead and begin that. So add a page, and I guess I'll just call this maybe applications of DFS. There's actually more than there's many different things you can do with DFS, but these are the two very common applications I can think of. Is just the first one will be a cycle detection. So I guess we'll go over that right here. So cycle detection. So basically, um, if a cycle is found in a graph. So for example, a cycle is something like this. I'll erase it, but I'm gonna first draw an example. So right there is a cycle because these edges right here form a cycle. So cycle is just a path that goes back. So we had, let's say we were at this node, went from here to here, here to here, and we go back to a node that's in our path. So basically that's a cycle essentially. So I don't think there's anything too hard to grasp what a cycle is. So basically, so in order to find a cycle, so if a back edge is found, then a cycle is present in the graph. So back edge, well, I mean, I guess maybe in CS477 you might learn about this in more detail, but a back edge is really just, I guess, an edge that goes back to a node that's currently in our path. So basically, we're going to have to do the following. So we're going to have to maintain these elements in order to be able to detect a back edge in our graph. So I guess structures needed, once again. So you have to maintain the following structures. So once again, we're going to have some type of a current node ID, which tells us what node we're currently on in our traverse. So we always have to have that for depth first search. So you can't avoid that. Of course, we're going to have our adjacency list. We can't really avoid that because that's going to really be our graph. That tells us which nodes connect to what other nodes. So this is really going to be our graph representation. So without that, you really can't do anything. Of course, our visited array, we definitely need to use this because we want to know which nodes we've been to, which nodes we have not been to yet. So we have to, of course, have that. And then our last structure we're going to have to use is going to be our nodes in path array, which is going to be a little different from our visited array. Because we have to also know, so having our visited array is not going to be enough to really know if it's a back edge. Because, for example, we had the following situation. Let's say we have this graph over here for a second. So this graph right here clearly has no cycles. So what happened is initially this would be marked visited. Let's say we go over here next, visited, and then we hit a dead end, we go back here, now we visit this node. We try to go to this node afterwards, but we've already marked it visited. So we can't really distinguish, is that really going to be a cycle? Because we've already been to this node, but that does not automatically imply a cycle. So we have to maintain what nodes are in our current path, because once we back up from a current node, then that node is not in our path any longer, which means that if we find an edge to that node, that implies, well, does not imply a cycle, that implies, well, we've already been there, so there's no point to go there, but it's not a cycle per se. So I'll explain exactly what I mean by that. I'll give an example here. So I'll draw the code out for this just to kind of be consistent. So let's go ahead and write the code for this. This is going to be a Boolean function this time instead, because it's going to return true if a cycle is found and false if a cycle is not found. So I'm going to say bool, I'm going to call it cycle, and I'll pass in the following parameters. So of course I'm going to pass in cur again, which is short for current, which is the node we're currently processing in this function. Then we'll of course pass in our adjacency list. Then of course we're going to pass in my bool visited array, and then my bool nodes in path array. So when we call this function in main, we would go ahead and of course you'd have our visited array allocated and our nodes in path allocated. And then we're going to set false to each element in visited and nodes in path. Because initially, none of our nodes is visited and none of our nodes is currently in our path. So of course, you would set each of these elements in these two arrays to be false, which makes sense. Okay. So we're going to now have the following. So of course, just like for our depth first search example, we're going to first check to make sure that this node has not been visited yet. So we're going to say if visited occur. If that's true, well then I guess return false, which implies that, well, this path leads to no cycles because you've already been here, so we're not going to expand from this node. So no cycles will be obviously found. Now, if it's not visited, of course, we're going to now mark this node as visited. We'll set it to true. And we're going to also set nodes in path cur equal to true as well. So this node is now in our current path. Now we don't have to really know the order of the nodes in our path. We just want to know which nodes are currently in our path. And I'll do an example. I'm not going to trace the code out as in detail like I did last week, but I'll just kind of trace this out. So of course, now we're going to have the following for loop, which is going to go ahead and call this DFS cycle function on every neighbor of cur to search for a cycle. So I'm going to have a for loop as always. So for node star I equals adj list cur. So we're going to traverse through all of cur's neighbors. And I is not equal to null. And then we're going to have I iterate through every neighbor. And I'm trying to think if I need any brackets. I don't think I have to have any brackets for this. I can probably do it without brackets. So anyway, so the first thing we'll do is check. So if nodes in path I arrow, I think I used ID last time for this, so I'm going to use ID over there. So this implies if a neighbor of I, that neighbor ID, neighbor node, sorry, is already in our path. That means we found an edge that goes back to a node in our path, which means we found a cycle. And we'll see this, how this actually works out as we traverse this or trace this code out on a board. But anyway, that implies a cycle was found, so return true. Now, if let's say it's not in our current path, then we want to go ahead and try to expand on that neighbor. So we're going to first check and say, well, if not visited ID, so if you have not gone to this node before, then we're going to go ahead and expand on this. So then we're going to go ahead and we're going to now call DFS or a cycle function on this neighbor. So if cycle I arrow ID ADJ list visited and nodes in path. So if I go ahead and call this function recursively right here, and it returns a true back to me, we'll then simply relay that true all the way back to the beginning. So really, it is DFS with a few extra bells and whistles. So if let's say we can't return true, so every neighbor we try to call DFS or cycle on, and none of them returns true back to us, that means, well, at least from this node cur, from cur at least, there was no cycles found. So maybe from its predecessor, a different path could lead to a cycle, but at least from cur, from that node, no cycles could be found from there. So then we're going to, of course, we're going to set nodes in path cur to false and then return false. So justification for this is as following. We go ahead and just sort of bracket there. So the justification for this, so we can see the entire code. Let me just make sure I can zoom out here a bit. There we go. So what happens is all we're doing is basically just we're at a node cur, and I want to try to expand on every single neighbor and try to find a cycle from that neighbor. If I find a direct edge as a back edge, cycle found return true. If not, I want to expand on that neighbor if we have not visited that yet and see if I can find a cycle along that path. If I do, then relay that cycle, relay true all the way back to main. If not, then try a different neighbor. If every neighbor of cur is not going to be a cycle, okay, fine. I have to back up from cur to the previous node and then try from there a different path. But when I return back, this node cur is no longer in my path because if I back up, I backtrack, right, return back to the previous node, then cur is obviously not in my current path anymore. And then return false, which means that, well, there could be a cycle somewhere else, but at least from cur, there was no cycle. So what happened is, for the previous function call, this returns false, which means it skips the return statement, and then we'll go ahead and try a different neighbor. So I'm going to go ahead and definitely trace this out so you can make more sense of this. And of course, in main, what I would do is let me go ahead and write the main portion over here as well, just so we can kind of visualize this. I'm going to have int main. And I'm going to assume we have all of our variables declared. We allocated our adjacency list, our visited array, and our nodes and path array. And we set every element in visited and nodes and path to all be false. And we correctly insert all of our nodes into our adjacency list. And we'll have the following loop that's going to call this function. So I'm going to say for int I equals 0, I less than, let's say we have a variable called vertices, which tells us how many vertices we have in this graph, I plus plus. And then I'll just have it very simple. I'll say if cycle I adjacency list visited and nodes path. I'll keep it sort of the same camel case. Then we're going to I can't write curly brackets for some reason. Okay, that one's pretty good. Cout cycle found. And I'm going to go ahead and break out of this loop. And then I guess int main returns 0 at the very end. So what happens here, I'm doing this loop again because I want to call this DFS or cycle function for every node, because in case, let's say from node 0, if not every single node can be reached, then I want to go ahead and restart DFS on a different node. So we could have an unconnected graph in this example. So from 0, some nodes could be not reached. So you want to go ahead and restart DFS on a new node potentially. That's why we have that loop. Otherwise, you could just say, we can make one function call only and just pass in cycle and then pass in 0 instead of I, but we do this for every single vertex. So in case, if let's say vertex 5 can't be reached from 0, then it would restart DFS on a new node. Okay. Let's go ahead and just sort of draw out the example. Let's go ahead and create a graph over here, and let's try to see how this function will work on this example. So I'm going to, I have to go back and forth, up and down in this OneNote notebook. That's fine though. So let's go ahead and create a few nodes in this graph. Let's say I'll try to, 8 nodes is a large enough example. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, I'm going to see if I can try to, let's see how I can do this. So maybe I'll have following edge, that one goes over there. Let's see, then we have this. Okay, let's see what else we can come up with. And so I guess we'll have our cycle right here. So we can see we have a cycle right there, but of course we're going to go through the motions and see how this code will actually generate this cycle. So I was going to determine the cycle using the code we had provided for that cycle function. And then we'll try this. Let's see. Hold on. Okay, I got this. Okay, so that, and let's do a few more. Add me one more edge, I guess. There we go. So this is going to be our example graph we're going to use. And I'm going to just use numbers as vertex IDs. So we have 0, we have 1, 2, 3, 4, 5, 6, and 7. So we're going to, of course, have our visited array below. So I'm going to create that array right here. And I guess maybe I could sort of, hold on. I'll go ahead and actually, I can maybe sort of, actually, I'm going to go ahead and I'll do this. So make it red. And then we'll have 8 elements. So we'll have all falses initially. It's a big setup time, actually, for the example. That's okay. So we should have the right number of elements. So 0, 1, 2, 3, 4, 5, 6, and 7. Perfect. I'm going to go ahead and copy and paste this. I have to redraw that. This will be my visited array. This will be nodes. I can write this nicer. Nodes in path. Okay. I think we're finally ready to go and do this example. I think I can try to zoom in on this a little bit so it's maybe easier to see this. So yeah, I think zooming in actually helps. So what's going to first happen is in our DFS stack, or sorry, not DFS stack. I'm going to zoom out a little bit here. We're going to have sort of our recursive stack over here. Remember, when we call a function recursively, we have a stack in the background. So we're going to first go ahead and call a function. We're first going to call cycle 0. Now, of course, we pass in other elements as well, not just only 0, but we're going to focus only on that cur value. Because every function, of course, we're going to pass in the adjacency list, visited, and nodes in path. I want to focus mostly on just that cur value. So right now, I'll go ahead and I'll mark, I guess red will mean that it's not visited. Let's go ahead and I'll just do this right here. And I'll use sort of, I guess also maybe use green to mark that it's not. Actually, I'll use green. I'll use green later on. Actually, no, I'll use blue. I'll use blue. Sorry, my mistake. I'm just trying to. I'll use blue to mark that it's not visited, and then green will be used to mark that it's in our current path. So let's go ahead and just do this. Okay. All right, perfect. So we first call cycle 0. So I'm just gonna skip. So I'm gonna first. I'll go to the code. Fine. So the code here will first check. So cur is 0. Visited 0 is gonna be false. So it's gonna skip this return. It will set visited 0 because cur in this case will be 0. It will set visited 0 to true, and nodes in the path also to true. So what's gonna happen now is we're going to mark this. Maybe I should use blue instead. Oh well. So what's going to happen here, we're going to mark this as now visited. So we're going to go ahead and sort of replace this with true, and same thing over here, which implies that we've already been to this node, and we're going to mark it as it's in our current path. So 0 is in our path right now so far. We only have one node in our path, so there it is. Okay, so from 0, we're going to try every possible neighbor. So we're going to first check. So the first neighbor we'll try will be 1, just because. We'll try 1 just because. So in our for loop, we have I equals adjacency list cur. So I arrow ID is going to be 1, because this is going to really just be the index or ID of a neighbor of cur. Remember, I is going to iterate through all of cur's neighbors, so I arrow ID will be just a neighbor ID. So IID is going to be just, in this case, will be 1. So we're going to see, is 1 in my current path? Well, nodes in path 1 is false, not my current path. And also 1 is not visited either, because this code checks is in our path, is not visited. So we're going to recursively call cycle, and we're going to pass in 1 into that function. Okay, so let's go ahead and do that. So we're going to go ahead and call cycle. We're going to pass in 1. So now we have to go to node 1. Looking at 1, so our initial check. So I guess you can probably take a screenshot of this code, so that way you can. I don't want to go back and forth like that. So you can take a screenshot, take a picture of this, so you have the code in front of you, so you can kind of use that to kind of help you trace this out. But anyway, I'm going to now go back to the very bottom over here and sort of trace out the example without going back and forth with the code. So what's going to happen now is that we're at node 1, and 1 is not visited. So we skip that return statement. So we're going to now mark 1 as visited. So we're going to put a red marker over there. And then nodes in path index 1, we're going to write this as true. And then we're going to mark it. Oops, sorry. I'm supposed to do this one first. First, I have to do this. And then we're going to set this to true. So I'll put a green marker here, implying that it is, in fact, in my current path. So right now, 0 and 1 is in my DFS path. Now, the order doesn't really matter. All we have to know is that those two are in my path currently. That's all we have to really know for right now. Okay, awesome. So looking at node 1, I want to see, well, okay, is there a neighbor of 1? So 1 has a neighbor of 5, and 5 has not been visited yet. So, and also 5, so remember, I arrow ID is going to be one of the neighbors of cur, or 1 in this case. So I arrow ID is going to be 5, because 5 is one of the neighbors. Remember, that I pointer, that node pointer I, is only going to iterate through all of cur's neighbors. Right now, 5 is a neighbor of 1. So we're going to now check and see, well, okay, so 5 is not in my current path, because nodes in path 5 contains false. Also visited index 5 is also false, so let's explore that node. So we're going to basically do the following. I'm going to now call cycle and pass in 5. So essentially, each function, so cycle 5 and cycle 1, returns a true or false value back to the previous function call. And using that return type, we're going to, of course, decide. So we'll go over that once we get there. But for now, it's going to return back. It returns back a value, true or false, back up to the previous function call, which will help, decide what that function will do next. So what's going to happen here is, okay, so from 5, we're going to now, let's see here. So from 5, we're going to go ahead and look at 5 first. So 5, visited 5 is actually false. We skip that return statement at the very top of our function. And we're going to mark this node as visited. So index 5 will be true. Keep it consistent, it'll be true. And 5 will be in our current path. So I'm going to now mark this as visited. And I'm going to also mark it as in my current path. So right now 0, 1, and 5 is in my current path at the moment. Okay, so now we can see here, let's look at that loop that's going to go through all of 5's neighbors. So that I arrow ID will pick a neighbor. Let's suppose that we first choose 2 as our neighbor. So 2 is not my current path, because nodes in path 2 contains false. And also visited 2 is also false. So let's go ahead and explore node 2. What's going to happen is we're going to call cycle and pass in 2 for that function. So for this function instance, cur in that function is going to contain 2. Looking at 2, so we enter that function call with node 2, and we check. So 2 is not visited. So we're going to skip that return statement, and we're going to basically mark this as now visited, and now my current path. So visited, and my current path. Now we're going to go ahead and explore and iterate through all the neighbors of 2. And in this case, well, there are no neighbors for 2. So we skip that return statement. Oh, no, sorry. We skip that loop. We jump out of that for loop in that function body. So at the very end of that for loop, well, all we know is that from 2, no cycle can be found from 2. So what we're going to do is we're going to basically set index 2 in nodes and path back to false. Because the purpose of doing this is that we're going to leave this node 2, which means that 2 is no longer going to be in our path. So what's going to happen is this function is going to end and it returns false back. I guess I'll use this color to kind of show the order of function calls. But returns false back to cycle 5. So we go back to cycle 5, and we last left off in this line right here. So I'll underline that. We last left right there in our function. So we called cycle 2. Return false, so we don't return true. We skip the return statement, and we're going to go ahead and jump to the top of our loop and try a different neighbor of 5. So returning a false means that, okay, the no cycle was found from 2, which means that there could be a cycle in our graph still, but we haven't found it yet. So, okay, fine. So now we're going to have to return back and return a false cycle 2. So we're going to have to now try a different neighbor. So 5 has the neighbor 4. Okay, so let's try to go to 4. So 4 is not in my current path. And also 4 is not visited either. So we're going to go ahead and go to node 4. So we're going to have DFS 4. We're going to try that neighbor. So we enter a function call, and we're going to first check 4 is not visited. So we're going to mark it as visited. And we're going to also mark it as in our current path, because 4 now is in my current path. Now, I guess to make things interesting, I could have chose 0 right now and then sort of be done, but I'm going to go ahead and choose 3 just to make this problem, so you can kind of see the full extent of how this code works. Because let's say, for example, maybe for some reason, the neighbor of 4, let's say the I arrow ID is going to initially be 3. Let's say for some reason, when we go through that for loop that goes through all the neighbors of 4, we happen to choose 3 as my neighbor. That could happen. So we're going to go ahead and try 3 instead, for some reason. And we're going to now go ahead and check. So 3 is not in my current path and not visited. So we're going to go ahead and call DFS on 3. So we enter this function call with 3. So we check visited 3. It's going to be false. We skip that first if statement up top of that function call. And we're going to mark this as visited and also mark it in my current path. So we're going to now set this to red and green. So now we have 0, 1, 5, 4, 3. They're all in my current path. The order doesn't really matter. All we care is that is it in my path. So, okay. So now we're going to have to go ahead and expand. So from 3, we only have one neighbor, which is 6. And 6 is not in my current path, and it's also not visited either. So we're going to have to go ahead and explore node 6. EFS 6. Like that. And then we're going to basically now, we're going to go ahead and call a function on DFS6. We're going to mark it as unvisited. Also mark it in our current path as well. So I'm going to go to my arrays over here and set this to true. I'm going to go a little faster here so we can go over the other example today as well. We'll go a little quicker. So from 6, again, we have nowhere to go except to 7. So from 7, we see a 7 is not in my current path, and 7 is also not visited either. So we're going to go ahead and call DFS 7. And we're going to mark 7 as visited, and also mark 7 in my current path. So once again, to make things interesting, I'm going to first have it where, oops, I should probably put this here as red means visited and green means in my current path. So from 7 to 2, we check. So 2 is not my current path, but 2 has been visited already, looking at our arrays. So we don't want to go to node 2. So having that nodes in path array helps us tell that if 2 is in my current path, because right now, we've already processed 2, but it's not on my current path. So there's no cycle from 7 to 2. So you have to be able to distinguish that has 2 been already visited, or is 2 in my current path, or both. But since it's not my current path, that's not going to be a cycle, so we just don't pick this edge. And the other neighbor of 7 is going to be 5. Looking at 5, nodes in path 5 contains true. So this edge right here is a back edge. This goes back to a node that's in my current path. So we don't have to know the order. All we have to know is that, oh, is there an edge that goes to a node? And if that node is in my current path, then it has to be a cycle. And we can see here, our cycle is right here, actually. That's our cycle. We actually have two cycles in this graph. We have actually 0 to 1, 1 to 5, 5 to 4, 4 is also a cycle. We have this cycle actually as well. So we found an edge that goes back to a node that's already in our current path. So if that happens, well, in that case, return true. Because in this situation, this actually happens. Because cur is going to be 7, and arrow ID will be 5, and nodes in path 5 is actually true, so we found a back edge, we found a cycle, so return true. And then what happens is, when we go back to our previous function call, DFS6, in DFS6, we were last stuck right here. And when I called cycle and I passed in 7, this right there returns true. So return true as well. So we'll just relay that true. Okay, fine. Let's go back to DFS3. In DFS3, we're last stuck also right here. And DFS3 ended up calling, let me just make sure, DFS6. DFX, and I passed in 6 into this function right here. It returns true. So if cycle ID was true, return true as well. We're simply just going to blindly relay true back to the previous function call. And the same idea, it's going to just simply relay true all the way up. All the way back to main. And in main, gets a true right here as well. Output cycle is found, and it breaks out of that loop. So all this code, all it does essentially is, once it finds a back edge, it returns true immediately, and it's going to relay that true all the way back to the beginning. If a false is returned, then it will try a different neighbor. And if every neighbor leads to a false and or it's already visited, we'll then return false back to the previous function. Returning false back really means, okay, the previous function will also try a different neighbor at that point. Returning false means, okay, just try something else. Returning true means just relay true all the way back. Because we saw over here, when I called cycle, I was on cycle 5, and I called cycle 2, it returned false back to me, which means, okay, so from 5, I tried 2, okay, try 4 instead, try a different neighbor. Which means that, okay, returning false does not really mean that there was no cycles at all. It just meant that from node 2, no cycles can be found. So we can try a different sort of path. And even a different path might lead to a cycle. That's basically how this works. So this is a little bit confusing code slightly, but anyway, any issues with this DFS modification of finite cycle? You, of course, can actually structure this a little bit differently to have maybe more variable, use a variable instead, but this is actually the simplest way I can think of. So this means you find a back edge, and then the other if means we're going to try to find, we're going to try to explore. And if you explore to a new node, if it returns true back to me, I found a cycle, return true back immediately. If no cycle is found, then try different, um, a neighbor. If every neighbor returns false and or our neighbor is visited, it will escape this for loop. It will return false, but it will first unmark this node, which means that this node is not in my path anymore. Returns false back to the previous function call, and for previous function call, it will try a different neighbor, because at least from this node, no cycle was found, and maybe a different neighbor might find a cycle. So the runtime for this obviously is going to be just O of E, just like the same runtime as DFS. This is really just DFS, but with a few extra modifications. So the runtime is going to be the same as DFS, because this really is just DFS traversal, but with some extra bells and whistles. So that's our first application of depth first search. Now I'm going to go over our next example, which is going to be another application of depth first search. Now this one will be a very good application. You will definitely never forget this this problem, because it's very applicable to right now to our current life, possibly. You'll see in a second. So topological sort of a graph. So basically, it's not really not really sorting. It's not like, quick sort or anything. They're not sorting. It's just a topological sort. It's really just an ordering. It's an ordering of nodes in the graph that respects the graph dependencies, and we'll go over what that actually even means in a second. Now, it only works, so this can only be done if the graph is a directed acyclic graph, or DAG, I guess is the abbreviation for that. So if a cycle is in the graph, then this cannot be done, and we'll see why in a second. So, okay, so I'll go over data structures, what we need for this, but the best way to think about topological sorting of a graph is courses at UNLV. So think of the following. So you have courses, and of course our mind is on courses because we're registering for classes right now. And, right now it's kind of a mystery of who's going to teach what, but at some point you'll probably know eventually. So obviously your mind is on this right now. So a course has prereqs, correct? So what we can do is we can think of this as sort of a course prerequisite graph. So basically what this really means is that a course number is a node, and then a prerequisite is an edge. And I want to list out the courses in the proper order. So what courses can I take at what time? So we want to list out what we can take, basically. So I'm not going to write the code for this, but really, and this is a very simple application of depth first search. So structures needed, of course, as always, or parameters needed, structures needed, or maybe parameters needed. I could probably also say parameters needed. Need a current sort of ID. of course, our adjacency list or matrix. You got to have that, of course. Our visited array. And we also need to have a last in, first out stack. So you can either create your own custom stack or use the STL stack. So of course, obviously, depth first search uses a stack for recursive function calls, but we can use a stack right now to maintain the nodes in our topological ordering. So basically, all we have to do, in order to get a topological order from the graph using DFS traversal, we need to push the cur ID onto the stack before returning out of the function. That's all you'd have to do. So probably the stack might be some reference parameter, most likely. So I'll put this here. A reference parameter is how you'd have this probably set up. That's all you have to do. So before you return out of the function, so take your DFS code, just copy and paste that. And before the function returns, just have that stack dot push cur. That's all you'd have to do, literally. That would be it. And then once the nodes have all been processed, the stack from top to bottom contains the topological order. So very easy to actually do this. A very simple algorithm, actually. So let's go ahead. And I have 20 minutes left, so I'm going to try to do this example quickly, so we should get this done probably today, because this is really not going to be a hard problem. Let's go ahead and do this right now. Okay, so I don't know the exact prereqs. You can, of course, help me out with this if I do get lost. They change every single semester, but I'll say for now we have 135, their starting point. Then I think we have 202. I'll highlight this. We have 202. Then we have 302. Then we have 477. Then we have 218, 219, 370. I know we have at some point we have 456 eventually somewhere down the line. Then we have 460 somewhere. Let me move this over here a little bit. Move this closer like that. It's not too out of whack. 326. Let me see. What's the prereq for 326? Let me know. I think it's what? Is it 302? You know what? Let's go ahead and just make up. You must have that before compilers for sure. I know you have 326 is before compilers, definitely for sure. I'll say 302 is a prereq for that. So I'm gonna go ahead and just sort of put the circles over here just to kind of create this graph. It's not too even, but I guess good enough. This might not be 100% accurate, but I'm just going to go ahead and just, I believe this is a prereq for sure. Then you must have 202 in order to take 302, I believe. You must have 202 for 218 as well. I think you have to have 218 for 219. 219 is needed for 370. I believe you need 302 as well for 370, I think. I know you need 302 for 477. And 460, I know that requires Talmud theory. I'm going to say 302 is needed also for, actually, hold on. I know 326 needed for 460. I'll go ahead and I'm going to have to, really? That's an odd prerequisite, but okay, sure. I'll add that in as well. And is that really it? What about, does 302 need also for 326 as well, or what about 456? I think you need 302 for this, I would imagine, right? I imagine you need this for 456. I think at least need that. I mean, I could be wrong, but I mean, this graph will do at least for our example. But I mean, let me know if I made a mistake with the prereqs anywhere here. I'm not sure the prereqs are. I know for a couple of them, but after a certain point, though, it's kind of all out of whack. So let's see. Maybe okay, let me go ahead and just make up some fake prereqs just to make this a bit more interesting. Um, I'll say 370 for 456. So this is not might not be accurate. So don't take this. This is just I'm making up some stuff here to make this a bit more interesting. So I guess interesting enough. I'll say 302 as well. I'll say you need this also. Actually, I think that might be it. I think I'm gonna go ahead and go with that for right now. I think this will be good enough. So if it's not the right prereqs, it's okay. It's not really important. I was trying to at least make it somewhat applicable to a real life application. But anyway, so we have the following graph. So each node will have a course number, and edge will be a prereq. And we can see here there's definitely no cycles in this graph. And if a cycle exists, then we can't do topological sort, which makes sense. But we'll go ahead and just do an example as to why that wouldn't work either. Maybe I can talk about that next time, but I at least want to go over just the example today. So let's go ahead and I'm going to zoom out of this graph so we can kind of see everything. So I'm going to have maybe the stack. I'm going to have the stack on its side actually because I'm going to have too much space over here to draw a stack out. So assume we have a stack on its side. It's tilted over. And there. This is going to be our stack. It's on its side. It's not, it's just like, so the top will be the rightmost element will be our top of our stack. No big deal. So when we first run our code, we're going to first, obviously, our starting node will be 135, and we're going to mark it visited. And then we're going to go ahead and pick a neighbor. We have one neighbor, which is going to be CS202. Go over here next. From 202, let's choose 218 next. So DFS, we just pick an edge. 218, sure. From 218, we pick an edge, 219. From 219, we try 370. From 370, we try 456. And then from Talmud 346, we try 460. So we just, that first search, we just pick an edge. We pick a neighbor. And now we hit a dead end. So we're going to return back from this function. We're going to first push 460 onto our stack before we escape. So we go back to the previous function call, which was 456, and we have nowhere else to go. So push 456 onto our stack. Let's go back to 370. Of course, we have to backtrack and go back to our previous node. So from 456, our previous was 370. From 370, there's nowhere else to go. So push 370. And then go back to the previous node, 219. So we go back to 219. From 219, okay, well, we do have another neighbor, which is 326. So we're going to go there next. And then from 326, we have only one neighbor, but we've already been to 460. So we have nowhere to go. So we have no other neighbors left. So we're going to first push 326 onto our stack and then go back to our previous node. So back to 219. So from 219, we tried 370, we tried 326, we tried both of those. So there's nowhere else to go. So we're going to return out of 219. We're going to first push 219 onto my stack and then go back to my previous node. The previous node was 218. So we already tried 219 from 218. There's no more other neighbors for 218. So we're going to push 218 onto our stack and then go back to the previous node, which was 202. So from 202, we tried the neighbor 218. Now we have to try a different neighbor, 302. And 302 is not visited, so we're going to go to 302. So from 302, we're going to try 370. Well, we've already been there, so we can't explore 370. Then our other neighbor for 302 is 456. Nowhere to go there either, so we can't go there. And then we have another neighbor, which is 477, which has not been visited. So let's go to 477 next. Now we're there. So, okay, we're going to have to go ahead and push 477 because we hit a dead end. So we're going to first push 477 and then go back to our previous node, which was 302, because we came from 302. From 302, we tried every edge, every neighbor. So no more nodes to explore from 302. So we're going to push 302 onto our stack and return back to 202. From 202, we have nowhere else to go. We tried 218, then we tried 302, no more neighbors left to explore. Push 202 onto our stack, return out of 202. 135, we picked that one neighbor, 202, nowhere else to go. We're going to go ahead and push 135 and return. And now our stack from top to bottom is going to be our topological ordering. So from our stack top to bottom, we're going to do the following. We're going to go ahead and just one by one pop an element. So pop 135, output it, then pop 202, output it, pop 302, output it, pop 477, output it, pop 218, pop 219, pop 326, pop 370, pop 456, and pop 460. This is going to be our topological order of our graph. Let's see our question here. Well, it's there because what happened was as we traversed this, we had 135. So we traversed it in this way. We went 135, then 202, then 218, 219, 370, 456, 460. We hit a dead end at 460, pushed 460 first, backed up to 456. We had nowhere else to go, pushed 456, and then 370 pushed that, went back to 219. So the idea was because it's the order which we traverse. So for example, I could have from 202, I could have chosen 302 first before 218. And then 477 would have been earlier in my stack. It would have been more towards the bottom. But I chose 218 from 202 before I chose 302 in that DFS traverse. That's why 477 is there in the stack, the way I chose it. And you could take actually 477 before 218 technically, because once you have 202 done, you can go 302, 477, and then take 218 after 477. That actually is a valid ordering. So it's there because that's the order I chose. And I chose 218 in his DFS traversal instead of 302 first. That's the reason why 477 is there. And of course, when we return out of a function, we push that node ID onto my stack first, and then we return back. So of course, there's more than one possible topological ordering. This is not the only ordering we have in this graph. I mean, for example, I could have, in my DFS traverse, I could have chose 302 first, and then returned back, and then tried 218. If I had done that instead, then a different topological ordering I would have gotten. So it depends on really what sort of neighbor you choose and what order you choose them when you're at a node and trying to pick a neighbor to expand your DFS search through. So it depends totally on what order you go. So for example, yeah, I could have chosen 302 first, and then it would have been different ordering completely. But it would have been a valid topological ordering. So all you have to do is for the algorithm, just run DFS like you always have. And before you return back from a function, you push that node ID or that cur onto the stack before returning out of the function. That's it. And then if you do that method, the stack from top to bottom is going to hold your topological order. That's really all there is to this. So basically, the runtime for this algorithm, of course, will again be same as DFS. It's OV. Same runtime. It's DFS with just one minor update. We just push cur onto the stack before the function returns. That's all you have to do. And then you have topological sort your stack from top to bottom is going to be the actual order of nodes in topological ordering. And we can see here that it does maintain the ordering because, for example, to be at 370, you must have 302 and 219 first. As we can see here, here's 370. We have 302 and 219 are before 370. So the idea is that we have to maintain that sort of that order basically. So if you have a case like 302 and 218 that they do not depend on each other, then any order would work. 302 first or 218 first. It doesn't really matter which one comes first because either order would work in that scenario. But this maintains that precedence. So for example, to be at 456, you must be at 370 and 302 first. As we can see in our order, 302 is first, then 370 comes next, and then we have 456. So we maintain that order still. So anyway, same idea, even for 460, you must have automata theory, 456, and 326 first, which we have those both there as well. So basically this ordering in blue maintains that's going to be a proper ordering of the nodes that maintains these prereqs basically. And if a cycle is in your graph, it will not work. I mean, for obvious reasons. I mean, think of the following graph like this. Or I mean, I'll draw it like this. So let's see. Let's take a look over here. Yes, university. Let's say it's a college, and then job experience. Actually, college internship, and then job. So they have the following graph like this. So imagine this scenario. Cycles in your graph. And the problem here is that then there's no topological ordering. There's a vicious sort of that cycle after college where you have a job to have experience, but you have to have experience to have a job, and that whole entire vicious cycle, that's what really happens for topological sort. Because in order to be in college, you must have a job first. In order to have a job, you must have internship first, and so forth. So there's no ordering in this graph. It can't be done. Because if you go in college first, let's say, oh, well, you must have a job first. To have a job first, you must have internship first. But you have to have a college before internship. So you can see that there's no ordering. If a cycle happens in your graph, it won't work. So we have a cycle. In this graph, it's that vicious cycle where after college, you'll have internship experience. So you get a job, you can get it, but you don't have an internship. But I guess in order to have a job, you must already have experience, but you have to have a job to have experience, or that whole thing. It's kind of like that. So think of that, and that's why. So no topological ordering exists for this graphs. Is that vicious cycle, which is really terrible. It's also terrible for topological sort as well. So those are two sort of pretty, I guess, basic applications of depth first search. Now, topological sort is used actually for certain shortest path algorithms. So if your graph has no cycle, then you can construct a topological sort of your graph and be able to construct a shortest path in faster time than the basic shortest path algorithms. But anyway, that's kind of really not really for right now in this course, but that's kind of it leads up to possibly in 477. But anyway, I guess that's it for today. So I guess take care, stay safe. Thanks for watching. Have an awesome rest of your day, and I'll see you on Wednesday.